Okay, so the plan for today is to finish up our one last little problem in differentials at the end of 310, and then start into chapter 4, applications of differentiation, where we'll start into 4.1 and 4.2, extreme values, maximum minimum values, and the mean value theorem. We'll probably get through 4.1 and maybe get started on 4.2 and then finish up 4.2 next time. Just quickly recall that the makeup video is available on YouTube, 311 hyperbolic functions. The examine practice exam is available. And this coming week, we have the midterm exam planned, and keep an eye out for that sample exam. I should have that posted this afternoon. Um, so I should have that up and available this afternoon. I'll send out an announcement with a bit more information and details and so on. But that exam will be available on WebAssign from 9 a.m. on Monday the 21st through 11:59 p.m. on Sunday the 27th. And as I mentioned last time, you can use a formula sheet. You can write, formulas, notes, etc., on front and back of a standard size sheet of paper. You can use a calculator, as long as your calculator is only a calculator, so no, computers or tablets or phones or anything like that as calculators. Scratch paper, and pen and pencil. Um, no open books or notes other than the formula sheet. Um, and like I said, no phones or tablets as calculators. All right. And the quote of the day for today is by chess grandmaster Daniel Naroditsky. Um, so one of his, he has a couple quotes that I like, but one of them is this idea that not all pieces need to be climbing Mount Everest at the same time. So kind of when you're developing your pieces in chess, you try to put them on active squares, but sometimes a piece ends up on a square where it doesn't have a lot of activity right now. It can come alive a little bit later in the game. That's perfectly okay. And I think, around this time of year, midterm time, midterm grades have come out, you have midterm exams, midterm projects. There's maybe a lot kind of happening at the moment. And I think this is a good reminder, right? If you try to go kind of 100% uh, in every aspect of life all the time, that's kind of how you end up getting burnt out. So, maybe you see your midterm course grades, you see what stuff is coming up the next couple of weeks, and make an active plan to, okay, I'll take it a little bit easy on this course. I'm pretty good here. I can, cut back my effort in this course a little bit over these next couple of weeks and boost my effort in that course to knock out a big, a term project or something like that that is important. I know that faculty tend to, want to pretend that students are like only taking our one class and they have nothing else going on in their lives, but we all know that that's not the case, right? You're balancing different class loads, you're balancing life demands, job, family, all those kind of things, friends and social activities. So, um, there are times where one of those needs the effort boosted, and maybe that effort has to come off of something else. And I think actively balancing that is as much an art as a science. And it's a very useful thing to practice and to learn. Okay, so moving on to 310, just really quickly recall that the linear approximation to y equals f of x near a is given by the tangent line. F of x for x is near a is approximately equal to the linear approximation L of x, the line that is f of a plus f prime of a times x minus a. One note that I think I forgot to mention last time is um, sometimes I'll get students, they'll write down an answer for a linear approximation and it turns out to be a nonlinear function, right? It's like, whatever, e to the x plus x squared, minus x or something like that. Your linear approximation should always be a linear function of the independent variable. Be a little careful here, right? F of a, f prime of a, these are function or its derivative evaluated at a. So these are numbers. That's a number plus number times x minus number. The only place that you should see an x popping up in here is x to the first power. If you're getting x squareds or e to the x's or something, there's a decent chance that you maybe made a mistake when you say, if you wanted the linear approximation near a equals 1, let's say, maybe you found f prime of x, and instead of going that next step and plugging in f prime of 1, getting a number and plugging it in here, maybe you actually just stuck f prime of x in there, right? And f prime of x might be like e to the x plus x squared, and then you've got a bunch of nonlinear stuff floating around. So we want to make sure that we evaluate the function and its derivative at the point of interest at x equals a up here to give us number plus number times x minus number. This is a linear function. We should only see x's coming in as x to the first power. And then a couple of notes here. This is really just a rearranging of the derivative. We just kind of chop off the limit, and we say that this is approximate for values of x near a, and rearrange a little bit to get this. So if you ever forget, wait, what was the formula for the tangent line? What was the formula for the linear approximation? Just take your definition of the derivative, get rid of the limit, and solve for f of x. F prime of a times x minus a plus f of a. That is exactly what we have here. So that's an easy way to remember the formula. If you remember the definition of the derivative, you have the definition of the linear approximation more or less built into it. And then we also said the differentials, well, this is just a very similar idea to a limit. F of a plus delta x is approximately L of a plus delta x, or that is just, I think I had this written wrong initially last time and had to kind of fix it on the fly, but L of a plus delta x is f of a plus f prime of a delta x. Or in other words, if we have a deviation on the input side of delta x, then the associated deviation on the output side is approximately, we might call it delta y, and we see that it's approximately f prime of a times delta x. So in a change in the input gets magnified in the output approximately by a factor of f prime at a. So that's another perspective on the derivative. Okay. And I think this is like two different fonts here. Sometimes it's OneNote will switch me to like some kind of strange math font. So sorry for the two fonts. If you're a graphic designer, it's probably driving you crazy, but it'll switch me back and forth between the Calibri or whatever the standard body font is and some kind of like Cambria math or something like that. I'm not sure why that works that way, but okay. So let's look at one last example in 310. The circumference of a sphere is measured at 84 centimeters plus or minus 0.5 centimeters and is used to estimate its volume. Let's estimate the maximum error in the volume estimate using differentials. So this might be, if we're making some big ball bearings or something, I guess these would have to be ball bearings for quite a large machine, but maybe we're making ball bearings and we're interested in, we have a tolerance for the size of our ball bearing. Let's say it's in terms of the circumference, and we're interested in knowing, how does that tolerance level affect the amount of material that it takes us, the steel or whatever it is, to make that ball bearing. Oh, I had my one screen unplugged for the last class, so it's always a little bit of an adjustment to switching over to writing on two screen mode. All right. So what is the answer here? Well, we see that we have a question about volume and we have information about circumference. I would like to write my volume as a function of the circumference. I know that my volume of a sphere is 4/3 pi r cubed. And I know that my circumference is 2 pi r. I can relate the volume and the circumference through the radius r. So r is c over 2 pi. And v then is 4/3. I've got a pi up top. And then r cubed is going to be what? C cubed over 8 pi cubed. And let's see, a lot of stuff is going to go away. So the pi on top cancels with one of the pi's on the bottom. So I have c cubed over pi squared. And then this 4 and that 8, they lose a factor of 4, and I end up with 6 pi squared. So I see that. I see that v of c is c cubed over 6 pi squared. Now my question is, what is v of c plus delta c, right? Here is my kind of circumference c that I'm anchoring on. And this is like a delta c. That's like a change in the input to this calculation. How does that cascade to a change in the output in our volume? So v of c plus delta c is approximately v of c plus delta v, or just v plus delta v. Or we see that that is v of c plus v prime of c delta c. Okay, so I need to find v prime of c as well. And that's not too bad. It's 3c squared over 6 pi squared, or that's c squared over 2 pi squared. Plus c squared over 2 pi squared delta c. So what is the maximum error in the volume estimate? Well, that is my delta v. That's how much the volume changes on the basis of this error in the circumference measurement. That's this thing evaluated at the particular circumference that we're starting at, 84 centimeters, as well as taking into account delta c. So when c equals 84 and delta c equals 0.5, delta v is going to be 84 squared so paranoid about writing fours because OneNote just loves the correct under the nines that I half the time end up writing them all wonky. So c squared 84 squared over 2 pi squared times 0.5. So this is the factor that we have to multiply our error in the circumference measurement by in order to scale that up to an error in the volume estimate. So that is our answer. And if we wanted to, we could plug that in the calculator, get an approximate answer if we wanted to. Any questions on linear approximations and differentials? Okay. I'm going to zoom in just a little bit here, make it a little easier for you to read, because we've got a lot of definitions and so on in this next section. So moving into chapter 4, applications of differentiation, and starting in 4.1, extreme values, sometimes called extrema. So one extreme value is an extremum, and multiple extreme values are several extrema, or just maximum and minimum values. And we have some definitions. F has an absolute or a global maximum at C if it's true that f of x less than or equal to f of c for all x in the domain of f. So this is like if I have a function that say does something like this. I might look at this input C here, coming up to this output f of C. And I notice that, and let me erase this little right tail over here just so we don't, so there's no real question about it. So we notice that if this is the domain of f from here out to here, there's no input that gives a smaller output, meaning smaller, meaning closer to negative infinity, than C. So my minimum value, my absolute or global, sorry, I was talking about maximum over here, I switched to minimum over there, but minimum is quite similar. So my minimum value, my absolute minimum value is this value here, f of C, and its location is at x equals C. And analogously for maximum, I see that for this C, maybe I'll call it C tilde. On the input side, I have an output f of C tilde. There's no other input in the domain of f that I see here that yields an output that is bigger than f of C tilde. So this would be, f of C tilde would be the absolute maximum of this function on this domain, and its location would be C tilde. So absolute max and min are maxes and mins over the entire domain. On the other hand, we have relative or local maxes and mins as well. So we would say that f has a relative or a local max or min if these criteria hold for x near C. So for instance, I might look at this point, and maybe I'll call this D instead. And I note that, well, this isn't a global maximum because I can go off to the right, say over here, and get larger outputs, or even off to the left over here and get larger outputs. However, let me erase a couple of these marks here. If I go just a little bit to the left, or just a little bit to the right, in either direction, my output decreases. So I can find some little open interval where kind of if I restrict my vision to that open interval containing D, then I do have something that, if I restrict my vision to this little open interval here, then I do have something that looks like a global maximum, but on this very restricted open interval. So that's what we call a relative maximum or a local maximum. It's kind of the king of the hill for these points near it, or it's like the big fish in the small sea, where this one is the global maximum. Of course, if a point is a global maximum, it's automatically a local maximum as well. If its output is bigger than any output in the whole domain, its output is certainly bigger than the outputs for the inputs that are near it. And then likewise for a local minimum, if we were to look at a point, let's say maybe like this one here, we'll call this E. Again, if I go far enough over to the left here, I can find outputs that are smaller than it. But if I stay pretty close, if I stay pretty close, then the outputs associated with the inputs near E are all bigger. So this value, this f of E, would be a local minimum, and E would be the location of that local minimum. I'm trying to be pretty careful with my wording here because we want to keep clear the distinction between the local or global or the relative or absolute max and min value versus its location. So the values of the max or mins are the outputs, and the locations are the inputs that yield those outputs. Now, something that, might irk you a little bit being a math class, this for all x and near c seems a little bit hand wavy or imprecise. What do we mean by this? Well, whenever we say for x near c, that actually does have a pretty standard definition. Sometimes it's also phrased as for all x in a neighborhood of c. So sometimes there's this idea of a neighborhood. Or sometimes it's said that for some open ball centered at c, or in just the real line, we would say for some open interval centered at c. And precisely what I mean by that is this, that there exists some positive number epsilon where we're considering all x in the interval c minus epsilon to c plus epsilon, that open interval there. So that's basically what we mean for all x near c. Now, I mean, I guess I've imposed that this is a symmetric interval. We might be able to relax that a little bit. If we wanted to be really pedantic, we might want to pick an epsilon bigger than 0 and a delta bigger than 0 and go c minus delta to c plus epsilon. But I think this is good enough for just about anything that we want to do. If we have a lopsided interval, we can either expand the interval so that it's symmetric, or we can contract the interval so that it's symmetric depending on the context, and get a symmetric interval that meets all of the same, criteria. So this is basically what we mean, is that there is some open interval containing the input of interest where all of the outputs are either, say, bigger than, or all the outputs associated with that interval are either bigger than or equal to the local minimum, or where all of the outputs are less than or equal to the local maximum. Okay, so we have a theorem, and my theorem has a typo in it. There we go. The theorem is the extreme value theorem, and it goes as follows. It says if f is continuous on closed interval AB, then there exists C and D in the interval AB, the interval closed AB, such that f of C is the absolute maximum of f on AB, and f of D is the absolute min of f on AB. Or this is sometimes just phrased as continuous functions on closed and bounded intervals achieve their extrema. And we did discuss this theorem already when we were talking about continuous functions. We discussed this, I think, a decent bit. So just a reminder of this theorem. We also have Fermat's theorem. This isn't the famous Fermat's last theorem, the one with the x to the n plus y to the n equals z to the n, has no integer solutions for n bigger than or equal to 3. The famous Andrew Wiles proof in was it the 90s, or last couple of decades that was proved. I think this might be sometimes called Fermat's little theorem. But this says that if f has a local extremum at c, that is the local maximum or minimum at c, and if f prime of c exists, then f prime of c has to be 0. That kind of makes sense intuitively, right? If I have c here, and if I want to come up with the graph of a function that has, let's just say, a maximum at c, the derivative exists, then, well, if it's differentiable here, it's got to be continuous here, right? We have a theorem that says differentiability implies continuity. So I need to draw a nice continuous function that's smooth and that has a maximum here. Well, if I do something like this so that I don't have a maximum and immediately to the right of C, I have a higher output. Well, then I don't have an extremum at C, right? If I do something like this where the derivative is not zero, again, I don't have a maximum at C. It kind of feels like I have to have a picture that looks something like that, where that kind of peak of that hill is right at that point there, and where I have a horizontal tangent line. And my drawing is slightly off as always, but I think you get the picture. So this kind of feels right. Let's try to go through a proof of this. Okay, so I have if these two things are true, then this thing is true. How can I argue this proof? I could maybe try to argue directly, but I could also argue the contrapositive if I can. Right, contrapositive, there we go. So here I have statement A and statement B. So if A, then B. What's the contrapositive? Remember, that has the same truth value as the original statement. Well, the contrapositive is if not B, if not f prime of C equals 0, then not A. So if I can prove this, then I'll have proven the original statement of the theorem. Okay, well, if f prime of C is non-zero, I suppose one thing that could happen is it could not exist. But let's suppose that f prime of C exists. So suppose f prime of C exists, and we'll use an acronym or initialism, depending on how you verbalize it, WLOG or WLOG. Without loss of generality, we'll suppose f prime of C, it should be non-zero, so we'll call it alpha a positive number. We'll assume that f prime of C is positive. Why is this without loss of generality? Well, you know, we could take it into two different cases. We could say case one, f prime of C equals alpha bigger than 0 and go through the proof. And then case two, f prime of C equals, let's say, beta less than 0, go through the proof. But it's going to be exactly the same proof, just with some signs reversed. So that's why when it's pretty clear that everything is going to work the same way in this case versus that case, if they're completely symmetrical cases, a lot of times we just say without loss of generality, let's assume the derivative is positive, because if the derivative was negative, that's not going to really change anything. Okay. But what is f prime of C? By definition, that is the limit h goes to 0, f of C plus h minus f of C over h. And remember, that is alpha, a number strictly bigger than 0. Okay, so what does this tell us then? Well, this tells us that there exists an epsilon bigger than 0 such that Remember, h is heading to 0, so for h, let's say less than or equal to epsilon, f of c plus h minus f of c over h. I think I have strictly bigger than here. Strictly bigger than alpha over 2, for instance. We're saying the limit of this thing equals alpha, a positive number. So this thing, I have to be able to restrict my input space small enough so that this thing is bigger than or equal to, say, alpha over 2, right? That's just coming right from definition of limit back in chapter 2. My function, let's call it, maybe to make it a little more clear, we can think of this as something like g of h. So my statement up here is that limit h goes to 0, g of h equals alpha, a positive number. And my statement down here is that I've got to be able to choose h small enough so that g of h bigger than alpha over 2. If g of h is limiting to alpha, at some point it's got to be bigger than alpha over 2. If it always stayed below alpha over 2 or always dipped below alpha over 2, then we could never have that corridor, so to speak, tightening down to an arbitrarily small number, which is what we need for the limit. So at some point, we got to have uh, inputs close enough to the limiting input so that this is true. But what does that get us? Well, that tells me that f of c plus epsilon minus f of c over epsilon bigger than alpha over 2 says alpha over 2, that is a 2. This tells me that f of c plus epsilon minus f of c is bigger than alpha over 2 times epsilon, or this says that f of c plus epsilon is bigger than f of c plus alpha over 2 epsilon, but alpha over 2 is a positive number, epsilon is a positive number, so this is bigger than f of c. So f of c plus epsilon is bigger than f of c for whatever epsilon we choose. So this is not a local or a global maximum. Because if I go a little bit to the right, I get a higher output. So it's not a local or global maximum. I could do something similar by changing that plus to a minus and going a little bit to the left. So just change epsilon to negative epsilon. That would put a minus here. Going through a similar argument, not a local or a global minimum either. So if my derivative is positive at that point, if it exists and is positive at that point, then that point cannot be a local or a global max or a local or global min. It cannot be the location of an extremum. Why is this without loss of generality? Well, if alpha was negative, I would have just gotten exactly the same results, but in a different order, right? This direction, the plus epsilon, would have given me the result with the minimum, and the minus epsilon would have given me the result with a maximum, right? My slope would be down, so it would be negative. So if I go to the left, I would increase, and that would mean it's not a maximum. If I go to the right, I would decrease. That would mean it's not a minimum. So that's why we just said without loss of generality, whichever direction our derivative is, positive or negative, we're going to, when we go one direction, we're going to go down, and when we go the other direction, we're going to go up. So it can't be a max or a min. So we've now shown this, which is the contrapositive of that. So we've proven the original statement that if f has a local extremum at c, and if f prime of c exists, then the derivative has to be 0 there. Okay, so Fermat's theorem feels a little bit clunky because we're also requiring that f prime of c exists, but we might ask ourselves, well, what about a situation with kind of an absolute value type deal, right? I mean, clearly this is a maximum, at least a local maximum, but if this is just, if it just keeps going off in these directions, then a global maximum as well. But since f prime of c doesn't exist, Fermat's theorem makes really no claim about it. Okay, so definition, a critical number of f is a number c such that either f prime of c equals 0 or f prime of c doesn't exist. And kind of rephrasing Fermat's theorem, if f has a local extremum at c, then either f prime of c equals 0. So if it has the local extremum at c and f prime of c exists, then f prime of c equals 0. That's kind of really the meat of Fermat's theorem. Or f prime of c doesn't exist. Or a little more succinct way of saying that is, if f has a local extremum at c, then c must be a critical number of f. Be really careful, this is one directional. We're not saying that if we found a critical number of f, if we found a place where the derivative is 0 or the derivative doesn't exist, then we have a local max or min there. We're not saying that. This is unidirectional. So if we have a local extremum, then that point must be a critical number of f. And this gives rise to our closed interval method. If we're looking to find the absolute or global extrema of a continuous function f on a closed interval AB, well, we know that it exists by the extreme value theorem. So if we're going to look for it, it's good to know it exists. It does exist because we have a continuous function on a closed interval. Extreme value theorem says that both the max and min exist. Both of them are achieved. Well, we go back to Fermat's theorem. If we have a local extremum, then it has to occur at a critical number. So what do I do? Well, if I think of my function on some closed interval, it has uncountably infinitely many outputs. That's obviously too many to search through by hand. But most functions are going to have a pretty small number of critical numbers on a given closed interval. If f has a local extremum, it must occur at a critical number. If I can just list all of the critical numbers and then check their outputs, I can just pick out the highest output to be the max and the lowest output to be the min, right? Okay, so to find global extrema of a continuous function on an interval, we first find all critical numbers on that interval. These are points where it's possible to have a local extremum. We also inspect the endpoints, A and B. I should say find all the critical numbers of f on AB and evaluate f at those points. So find all critical numbers of f on AB and evaluate f at those points. So I have potential input-output combinations that could be global max or global min. Not necessarily, but they could be. I also investigate AF of A and BF of B. These are also places that we could have an absolute max or an absolute min. Why do we have to check these endpoints? So I always like the little anecdote. My wife is from Kansas, and if you've ever been to Kansas, it's very flat, like kind of shockingly flat. Once you get across, into Illinois maybe or across Illinois, things start to flatten out, and you like just look horizontally and you can see the horizon instead of having to look up and look over the mountains to see the sky. So she always kind of jokes that, if you look at Kansas, say here's the ground Kansas, here's east and west. And then you have Colorado, which of course is famous for the Rockies, right? The highest point in Kansas is like everything is really flat. And then as soon as you get over here, you start to get into the foothills of the Rockies. And so the highest point in Kansas is like the westernmost edge of Kansas because that's where it's heading off to the Rockies. So even though, you might have a small like hill or something like that over here, the foothills of the Rockies are much taller than that. So we need to check our endpoints because we could have a function like this. And maybe this is our closed interval that we're looking at. We could have the maximum output right here at one of the endpoints. So I find my critical numbers of f. I figure out what are the inputs where either f prime is not defined or where f prime is 0. I find the associated outputs with those inputs. And then I also list a comma f of a and b comma f of b. Those are all the places that I could have a global max or a global min of this function on this interval. In other words, my global max and global min cannot occur anywhere but places that I've listed in parts 1 and 2. And then I just take from parts 1 and 2, the maximum output has to be the global max, and the minimum output has to be the global min on that interval. All right, let's go through a couple of examples. Let's find the absolute max and min of g of t equals absolute value 3t minus 4 minus 7 on t in -3 to 2. Okay, so let's get a picture of this. So absolute value of 3t minus 4, I see when t is what, 4/3. That's when the absolute value has 0 input into it. So 4/3. At 4/3, I have an output of -7. And I have something that looks more or less like that. So I do see that this point here where we have a derivative not existing is in the interval under consideration. So my critical numbers, t equals 4/3 is one of them, and g of 4/3 is -7. Do I have any other critical numbers? Well, no, I can see that to the left of 4/3, I have 4 minus 3t minus 7. That derivative is just going to be -3. To the right of 4/3, my derivative is going to be +3. There's no choice of t that could make a -3 or a +3 into a 0. So no other critical numbers. I could check the endpoints now. T equals -3 and t equals 2. As kind of a side note, if you forget about the endpoints, if you forget to check them. And remember, we're looking for an absolute max and an absolute min. I mean, the fact that we only got one critical number, at best, this could be either an absolute max or an absolute min, but not both. That's pretty suspicious, right? Because how am I going to get both an absolute max and an absolute min out of just one critical number, out of just one potential extremum? Uh, so if we forgot to check our endpoints, that's a little bit of a reminder in some problems that you got to check your endpoints. In some problems, we don't get a critical number at all. We get no critical numbers, and then just the endpoints. One of them is the absolute max, one of them is the absolute min. Okay, so my endpoints, these are the inputs I want to evaluate. G of -3, G of 2. So G of -3 gives me what? -9 minus 4 is -13. Take the absolute value, +13. And +13 minus 7 is +6. And G of 2, 3 times 2 is 6. Minus 4 is 2. Absolute value is 2. Minus 7 is -5. So if I did all my arithmetic right, that is what we should have come up with. And now I see the maximum output is 6. So I have an absolute max of this function on this interval, of course. So if I change the interval or change the function, it'll change, but an absolute max of 6 that's located at t equals -3 at my left endpoint. And I have an absolute min, the smallest output that I see, absolute min of -7, located at what? T equals 4/3. And there we go. Again, make sure that you're careful about whether the question is asking for the value of the absolute max or min, or whether it's asking for the location, or whether it's asking for both. So the value, for instance, of the absolute min is -7, and its location is t equals 4/3. And similarly for the max. Any questions on any of this? Okay, let's take a look at this function. H of x equals absolute value of x squared minus 9. We're looking at the interval -4 to 1. So let's again try to get a picture of this drawn. I know that x squared minus 9 looks like this, right? But absolute value says take what's below the y-axis and make it positive. So let's say here at 3, here at -3. I want to take this stuff that's below or did I say the y-axis? Below the x-axis. I want to flip it up and make it positive. And then the stuff that's outside, that's to the right of 3 or the left of -3, that was always positive to begin with. So it should be symmetric. It doesn't look quite so symmetric, but I apologize for my artistic skills. Let's just get rid of these little dashed lines down here. I guess we can get rid of all of this, really. Okay, so we've got an idea of our picture. We can, maybe even pretty quickly guess at what the extrem are going to be. But we have to be a little bit careful. We are given a particular interval to work with. And of course, I need a little more area to the left, and that's exactly where I did not give myself any more area. So I'm going down here to -4, but only up to +1 or so. Or, well, not or so, but up to +1. So, I mean, my function is not differentiable at +3. If I was looking over a wider interval, I might be interested in evaluating my function at +3 or considering that a critical point, but that doesn't count here. It's for this one, we're only looking at looking for critical numbers between -4 and 1. Okay, so critical numbers. Well, I definitely see that x equals -3 is a place I'm not going to be differentiable. So x equals -3 is going to be a critical number, and h of -3 is 0. I can probably guess that at x equals 0, I'm going to have a critical number, but I can also check that. I see that h of x, well, this is a piecewise function, right? Between -3 and 3, it's going to be 9 minus x squared. And it's going to be x squared minus 9 otherwise. I'll just say else. H prime of x is going to look like plus or minus 2x. And if we set that equal to 0, we see we get a second critical number, x equals 0. Let me actually try to lasso this and move it over a little bit so we can keep our critical numbers all kind of nicely organized here. There we go. So we see that h prime of x is going to be plus or minus 2x, depending on what piece we're on. If we set that equal to 0, that gives us x equals 0. So on this piece, we have a critical number, as we would expect from the picture, right at 0. Nice horizontal tangent there. So x equals 0 is another critical number, and h of 0 is absolute value of -9 or just 9. Those are our two critical numbers. We check the endpoints as well. X equals -4 or x equals +1. H of -4 is absolute value of 16 minus 9, or that's just 7. And h of 1 is 1 minus 9, -8, and absolute values is 8. So in this example, neither our max nor our min occur at the endpoints. They both occur at critical numbers. So because 9 is the biggest output of any of these four, that's our absolute max. And it's at a location x equals 0. And similarly, our smallest output is 0, absolute min of 0 at x equals -3. We don't want to say at both x equals -3 and +3, again, because we're restricting our attention to this interval -4 to 1. If we were looking at -4 to +5, well, we would want to say at x equals -3 and +3. We can have multiple locations that achieve the same absolute minimum or multiple locations that achieve the same absolute maximum. That's perfectly acceptable. In this case, though, because we restricted our attention to -4 to 1, uh, this +3 is not on our radar. We don't list it as another location of an absolute min. Any questions so far? Okay, so here's another function, f of theta equals 2 cos theta plus sine 2 theta, and an interval of interest, theta in 0 to pi over 2, looking for absolute max or min. This is a function that's probably going to be a bit harder to graph, so maybe I'll forego graphing and we'll kind of just trust the algebra here. Mhm. Okay, so first let's look for critical numbers. Is there going to be anywhere that f prime doesn't exist? No, cosine and sine derivatives exist on the whole real line. So f prime doesn't exist. There's going to be no contribution from that. So we're going to look for where is f prime equal to 0? Where is f prime of theta equals 0? Well, f prime of theta is, well, that's negative 2 sine theta plus 2 cos 2 theta. The sine of stuff differentiates the cos of stuff, and the chain rule pops out a factor of 2. And I want to know, when is this 0? Okay, so this isn't the easiest trig problem to solve. But one thing that I could do, I could also come up here, right? I note that sine of 2 theta is 2 sine theta cos theta. I could have used the product rule there, or I could use my doubling identity on the cosine. For these trig problems, there's usually more than one approach to get the solution. But cos of 2 theta is cos squared theta minus sine squared theta. Make things a little easier. I know I can divide out a 2. Let's just do that right away. So I probably shouldn't cancel them out like that, but because that would say f prime of theta equals something without the 2's. But just in terms of this equation here, those 2's can go away. So I have negative sine theta plus cos of 2 theta, or that's plus cos squared theta minus sine squared theta equals 0. When I have a trig equation like this where the arguments, where the inputs into the trig functions are different things, really my only hope of getting a solution to that trig equation, I mean, unless I come up with some completely ad hoc way of doing it, but my my own my main hope, I should say, I guess, is using some identities to make all of the arguments the same thing. So now we at least have everything as just functions of theta. My next big goal is to take all of my different trig functions and turn them into the same trig function. That's super helpful as well. I see I have a sine squared and a sine term, but I have this cos squared term that sticks out kind of like a sore thumb. Can I change a cos squared into something related to sines? Well, yeah, I can. Cos squared is 1 minus sine squared. And what can I do here? I have negative 2 sine squared theta minus sine theta plus 1 equals 0. And then I'll just go through and change the signs here. This will be a plus sine theta. We can get rid of the minus in front there. And that'll turn into a minus 1 at the end there. So that is the equation I need to solve, right? Again, with a lot of these calc problems, not all of them, but some of them like this one, there's a lot of algebra work, a lot of geometry work. We did an important step here where we took the derivative. Um, but now we're going through all of the algebra and the trig to actually solve the equation. Okay, and what's the trick here? Well, let say u equals sine theta. So I have 2u squared plus u minus 1 equals 0. Let me just give myself a bunch more room here. And I want to factor this. Let me see if it factors nicely. 2u squared can only factor into 2u times u, and 1 can only factor into 1 times 1. I need one of these binomials to have a minus and one to have a plus, and I want to net out a plus u. So I want a plus 2u from the outers and a minus 1u from the inners. Or this tells me either 2u minus 1 equals 0, so u equals 1/2, or u plus 1 equals 0, u equals -1. Or in other words, sine theta is 1/2, or sine theta is -1. If we're looking on the interval 0 to pi over 2, the first quadrant, that's what sine looks like. No solutions to sine theta equals -1 on this interval. Of course, there are solutions outside of this interval, but not under our interval consideration. We do see that there's going to be a first quadrant solution to sine theta equals 1/2. I know that I have a 1, 2, √3 triangle, and this is a 30, 60, 90 triangle. For some reason, I just always like to think in terms of degrees in these special triangles. So 30, 60, 90. And I know that 30 degrees, well, that's really pi over 6, and 60 degrees, pi over 3. So I'll keep that in the back of my mind. And sine, well, SOHCAHTOA, sine is the opposite of hypotenuse. Sine being 1/2 tells me I'm dealing with an angle of 30 degrees, or pi over 6. It was an awful lot of work to get a single critical number, but that is our one and only critical number on this interval. I don't have to find any other, any other solutions in other quadrants, or any other solutions that are, plus 2k pi kind of things, because we're only dealing with the interval 0 to pi over 2, only dealing with the first quadrant. So theta equals pi over 6, the only relevant solution to this equation. And maybe I've got a lot of random stuff written on here, so I'm gonna write that in a different color just to keep it straight. Theta equals pi over 6 is our critical number. And now we got to find f of pi over 6. Nicely enough, I think our little triangle down here is going to help us. F of pi over 6, what is that? That's 2 cos theta plus sine 2 theta, or that's 2 cos pi over 6 plus sine of 2 theta, or that's pi over 3. So that's twice cosine of pi over 6. Cosine is adjacent over hypotenuse, √3 over 2. And sine of pi over 3, the angle is different, so be careful with that. Sine of pi over 3, sine is the opposite of hypotenuse, √3 over 2 as well. Or this ends up being 3 √3 over 2. Okay, that was a lot of work to get our critical number, but we did get our critical number and we evaluated it to get the output at that critical number. Second, we check the endpoints. It's really easy to forget to check the endpoints after you do that much work and, kind of lose track of the overall strategy, but check the or check for critical numbers, get the critical numbers, evaluate them, check the endpoints, and then look for maxes and mins. So my endpoints are theta equals 0 and theta equals pi over 2. What's f of 0? 2 cos of 0, that's 2, plus sine 0 is 0, that's just 2. And f of pi over 2, cos of pi over 2, well, that's 0. Sine of 2 times pi over 2, where that's sine of pi, is also 0. This is 0. Okay, so switch to a different color here. There we go. The third thing we want to do is we want to look for the minimum output. Well, pretty clearly the minimum output is 0. Absolute min of 0 at the location pi over 2. And now we want to look for a maximum output. 3 root 3 over 2. Well, what's that going to be? So 3 root 3 over 2, is that bigger than 2 or less than 2? So 3 halves is 1.5. And square root of 3, well, 1.5 squared is 2.25. So this is going to be bigger than 1.5 times 1.5, which is 2.25. So 3 root 3 over 2 is going to be bigger than 2. It would be a real shame if we went through all the trouble to find that critical point and it did not end up being one of our extrema, but in this case, it is. 3 root 3 over 2 should be bigger than 2.25, which is bigger than 2. So let me draw that circle so it's not covering up our number we did all that work for. We have an absolute max of 3 root 3 over 2 at theta equals pi over 6. Kind of shimmied that in there, but there we go. Any questions on finding absolute maxes and mins? And I guess I should have noted, I didn't say this explicitly. I probably should have said this explicitly just to be very clear, but this closed interval method only works for continuous functions. So these were all continuous functions, even if g and h were not differentiable at some points. But these are all continuous functions. If I had a function with a big jump or something, or shot off to infinity, closed interval method, uh, it would not be appropriate to use there. And I was smart and I actually wrote this thing and then captured it and then pasted it here as a picture. So as I was, entering and going up and down, it was tracking along with us. So I thought of that beforehand. So this example, let's consider this following diagram. Here we have a weight that is moving along the ground. It's sitting on the ground. It's made of some material that has some friction with the ground. And mu bigger than 0 is the coefficient of friction. We have a rope attached to the corner of this weight, and we want to pull on the rope, and we want to pull at an angle theta. Now, kind of the interesting thing about this system is that we could pull the rope just straight sideways, but then kind of all of the weight would be contributing to the friction. It's pushing down, making more friction. So if I just pull it straight sideways, theta equals 0, I'm pulling against a lot of friction. If I were to pull like directly up, Well, if I pull directly up, there's no friction in that direction. I'm only pulling the weight up, but I also don't really move the weight at all. If I want to get the weight moving to the right, so if my goal is to move the weight this direction, I might choose an angle theta. I might choose to pull at a certain angle so that kind of, in some sense, part of my effort is being contributed to lifting the weight off the ground and reducing the friction. And part of my effort is contributing to getting the weight moving forwards. And it turns out the force required to get the weight moving ends up being given by this equation. F of theta equals mu w over mu sine theta plus cos theta for theta between 0 and pi over 2. And we want to argue that the force is minimized when tangent of theta equals mu. So that is our goal here. Let's take a little short digression and show where all of this comes from. So if I have my weight here, it's kind of pushing down with weight W. And I have my force here at elevation theta, pulling kind of like up and to the right at angle theta. If I look at my force elevated at angle theta, I see that the horizontal component of force is going to be F cos theta and the vertical F sine theta. Where does that come from? Well, if I just called this maybe X and this Y, I would see that cos theta equals X. So cos theta equals adjacent over hypotenuse, that's X over F, and X equals F cos theta, and then similarly for the vertical component. So that's where that comes from. Oh, small eraser. There we go. So my force breaks down into a force, whoop, force pushing that direction. F cos theta. I'm not having good luck with my pen today, or my writing skills, one of the two. And this direction, F sine theta. So my net, say, downward force is going to be something like W minus F sine theta. And this is so here's my friction between the two surfaces. This is what's contributing to the friction, W minus F sine theta. Right? When theta is 0, sine of theta is 0, and all of the weight is pushing downwards, contributing to friction. When theta is 90 degrees, pi over 2, sine theta is maximized, and then I have the minimum weight pushing down, contributing to friction, and somewhere in between, I have a balancing of those two extremes. So we need, what do we need? F cos theta, the horizontal component of the force, to be greater than or equal to the friction that's holding this block in place. And that's what the friction coefficient mu is. It's mu times that force there. W minus F sine theta. Need a little more room here. And we're looking to solve for F. So what do I get? F times cos theta plus mu sine theta bigger than or equal to mu w, and f is, well, I suppose f bigger than or equal to get it moving, mu w over cos theta plus mu sine theta. So that's where all of this comes from. That's where this equation comes from. That's kind of a side note. You wouldn't need to know that. You would, if this was on a homework problem or an exam or something, you'd be given this. But I figured since a lot of you are going into engineering, this might be something that, you've either seen in an engineering class or that you'd be interested in. Okay, but back to the math programming. We want to show that f is minimized when we choose a theta such that tan theta equals mu. So I have f of theta. I'm going to look for a critical number. So I'll start by differentiating. F prime of theta is, well, my numerator doesn't actually have any thetas in it, so that's just mu w times stuff to the -1 is -1. I'm going to need more space than this. So mu w times minus stuff to the -2 times the derivative of that stuff. The derivative of mu sine theta is mu cos theta, and the derivative of cos theta is minus sine theta. If I kind of rearrange this so it's a little nicer, I see I get negative mu w mu cos theta minus sine theta over this stuff squared. And I'm asking, when is this 0? I guess two ways I could look at this. I can multiply through by the denominator, divide through by negative mu w, or I can just realize the only way this fraction is 0 is when this parentheses is 0. So that says that mu cos theta minus sine theta equals 0, which says that what? Sine theta over cos theta equals mu equals tangent theta. So I have one critical number. We have theta such that tan theta equals mu. And maybe I'll call this, I don't know, theta star. And let's go the extra mile here. I think, we'd be tempted to just stop here. And, it does kind of make sense to stop here. But let's go the extra mile and try to work through this kind of in full detail. We found a critical number, but let's evaluate our function there. So f at theta star is f at the choice of theta where tan theta equals mu. So I need to evaluate sine theta and cos theta when I know tan theta. So this is also kind of a good review of a bit of trig. So if this is theta, tan theta is SOHCAHTOA, opposite over adjacent. So I can make like a mu there and a 1 there. And then my hypotenuse would be root 1 plus mu squared. So this is the triangle associated with, or a triangle associated with tan theta equals mu. This or similar triangles. So f of theta star, what is that going to be? Well, it's mu w on top. that doesn't change. On the bottom, I have a mu sine theta. Sine theta, sine is opposite over hypotenuse, mu over root 1 plus mu squared. And then plus cos theta. But cosine theta is adjacent over hypotenuse, so that's just a 1 over root 1 plus mu squared. Let's get a little more room here. All right, so what do I have? I have mu w over, in the denominator, I have mu squared over root 1 plus mu squared plus 1 over root 1 plus mu squared. That's mu squared plus 1 over root 1 plus mu squared. But I lose just a half power off the top and bottom of that. Mu w over root 1 plus mu squared. So for this critical number, this is my output. Maybe I've kind of run out of colors. Maybe I'll circle them in red, just so we can pick them out a little better. So the red box is my critical number. It's my location of my solution potentially. And the red circle is the value of that, hopefully, minimum. What else maybe we want to check? Well, we probably also want to check the endpoints, right? F at 0 and f at pi over 2. So f at 0, sine of 0 is 0, cos of 0 is 1. That's mu w. And f at pi over 2, cos of pi over 2 is 0, sine of pi over 2 is 1. That's mu w over mu. Or just w. Now, I don't know which of mu w and w is bigger, because I guess the friction coefficient, I think, can be any number. I think it could be less than 1 or bigger than 1, I'm pretty sure. We could also make the argument that, maybe the physics that we're discussing here kind of breaks down with theta's pi over 2, because we're just pulling the thing straight up. Right, when we're pulling the thing straight up, we're just lifting the weight. So as far as, these two values compared to one another, I'm not really sure. However, if I look at the output, mu w over root 1 plus mu squared, I know that root 1 plus mu squared is bigger than 1. So mu w over root 1 plus mu squared is less than mu w. Mu and w are both positive numbers. That's important. So root 1 plus mu squared is bigger than 1. The denominator is bigger than 1. So the whole fraction is less than just the numerator mu w. So I know that I don't have a minimum at 0. I know that if I pull up at a little bit of an angle or some angle, I can pull with less force than if I pulled straight horizontally and still get the thing to move. So I don't know which one of these is a maximum, but I know that I don't have a minimum at 0. I know that my minimum force needed is not mu w. It's going to be less than that. What about w? Well, I also know that root 1 plus mu squared is bigger than mu. If I take mu, square it, add 1, and square root it, that's going to be bigger than mu. Because square root of mu squared is mu, right? So if I put a larger input into an increasing function, square root of x, I get a larger output. Well, if root of 1 plus mu squared is bigger than mu, then this output up here is going to be less than mu w over mu, or it's going to be less than w. So this one is also not a min. I don't know which one's a max. I'm pretty sure, like I said, I think friction coefficients can be less than one and or bigger than one. So I'm not really sure, uh, but as far as a min, the math is clear. This is our absolute min force needed, and this is the direction of pull, or in other words, this is the location of that absolute min. So we should pull at, arctan mu at that angle, and we would need to apply this amount of force to get the thing moving. Any questions on anything? So I kind of hope that, I know that it was a couple of chapters, almost entirely chapters 2 and 3 of very mathy kind of content, but I hope we're starting to work our way into some material with maybe related rates or with some of these more physics type problems that um, where you can see the more direct relationship to, say, your engineering or physics or your applied classes. Right. Any questions so far? Any questions on section 4.1? I think we'll break for today because to introduce the idea of Rolle's theorem, I kind of want to hit the mean value theorem at the same time. Um, so I figured we wouldn't get, all the way through section 4.2, but I want to hit mean value theorem when Rolle's theorem is still fresh in our minds, because we're going to see that Rolle's is just a special case of the mean value theorem. Mean value theorem is generalization of Rolle's. So I think we will save that till next time and end a few minutes early today, unless there are any questions.